let's just dive straight into this. Welcome back to another explainer. Today, we're tackling what is honestly one of the most frustrating, high-stakes mysteries in all of electronic design. We are talking about electromagnetic compatibility, and specifically, mastering capacitive coupling and the strict math behind crosstalk. Now, if you're designing aerospace hardware, automotive communication buses, or high-speed printed circuit boards, you already know that invisible interference can absolutely destroy a system. So by the end of this explainer, you're going to have a concrete, mathematical intuition for exactly how this invisible coupling happens. And more importantly, you'll have the exact formulas you need to mathematically armor your circuits against it.
So picture this real-world engineering mystery. You've got two wires. They are perfectly insulated. They are totally isolated, absolutely not touching. Yet, a high-speed signal spikes on wire A, and suddenly, wire B throws a fatal data error. It makes you stop and ask, how does a circuit interfere with another completely separate circuit when there is absolutely zero physical contact? Well, the answer lies in the invisible electric fields, bridging the physical gap between them. To really understand how this happens, we need to look past the surface of the copper wire and zoom straight into the physical space between them. Capacitive coupling, which is sometimes incorrectly called electrostatic coupling, even though these fields are highly dynamic, is the interaction of electric fields between circuits. When a voltage changes on a conductor, it creates a fluctuating electric field. If you have an insulating material or dielectric in that space, even if it's just air, the neutral atoms within that material actually distort into electric dipoles. I want you to imagine those atoms stretching like tiny rubber bands under tension from the electric field. This rapid stretching and shifting physically transfers energy across the gap. In engineering, we call this displacement current. To permanently lock this in your mind, I want you to think of the invisible tuning forks analogy. If you strike a physical tuning fork, acoustic pressure waves travel through the air and force a completely separate tuning fork to start humming in sympathetic vibration, right? Capacitive coupling works the exact same way, but instead of acoustic pressure, it's electrical pressure, voltage ripples. These voltage ripples stretch and compress the electric field, which literally forces the electrons in the neighboring wire to shift in perfect sympathetic vibration. Now, translating that physical reality into engineering math, we rely on an equivalent circuit model. We have to take that physical air gap, the space where our tuning fork electric fields are interacting, and replace it mathematically with a mutual capacitance. We'll call this C sub m. So the physics of the electric field acting on the second wire is modeled simply as a phantom current generator, injecting that displacement current directly into the receptor circuit. All right, so the absolutely crucial point here is calculating exactly how much noise voltage, V sub n, is actually getting injected. For most practical low-impedance circuits, we pull this foundational equation from Ott's electromagnetic compatibility engineering. Let's break down the core variables driving this equation step by step. First, we have J omega. Omega is the angular frequency of the noise source. This tells us the coupling is directly proportional to frequency. Basically, the faster your signal edge rate, the louder that tuning fork rings. Next up is R, the resistance of the affected circuit to ground. Think of R like a kink in a water hose. If resistance is higher, the displacement current builds up much higher pressure, which means a higher noise voltage. Then we have C12, the mutual stray capacitance between the conductors. And finally, V1, the magnitude of the aggressor voltage. Let's assume you can't change the aggressor's voltage or frequency. That means you really only have two ways to fix crosstalk. You lower the receiver's resistance to ground, or you decrease the mutual capacitance C12. Physical separation is how we drop C12. Separating the conductors drastically drops the coupling, but the relationship isn't linear. For standard 22-gauge wire, almost all of your meaningful attenuation occurs in the very first inch of separation. Moving them from a quarter inch to 1 inch apart gives you a massive drop in noise. But moving them from 3 inches to 4 inches barely makes a difference. That first inch is absolutely your best defense. But hold on, because here is the critical engineering gotcha that trips up countless designers. Everything we just calculated perfectly assumes a relatively low resistance to ground. But what happens if you route a signal into a high-impedance input, like a standard CMOS gate? The noise voltage completely stops climbing with frequency. It hits a hard ceiling and just flattens out. So why does the math suddenly change? Let's actually compare the math for both states. When resistance R is very large, it acts like a totally blocked pipe. That phantom displacement current can't flow easily to ground, so our first equation completely breaks down. Instead, the circuit mathematically transforms into a simple capacitive voltage divider. The new equation becomes V sub n equals V1 times C12 divided by the sum of C12 and C2G. Notice what is completely missing from this second equation: omega. The frequency variable is literally gone. In high-impedance circuits, capacitive crosstalk becomes completely independent of frequency, but it hits a much larger magnitude. If you try to use the low-impedance formula on a high-impedance circuit, your math will be completely useless.
Okay, so practically speaking, how do we mitigate this? For PCB traces, controlling skew and adding physical separation is paramount. For cabling, your mind probably jumps straight to twisted wire pairs, but here is another major gotcha. Twisting a pair of wires together inherently eliminates inductive coupling, but it does virtually nothing to eliminate capacitive coupling unless the circuit is perfectly balanced. To truly kill capacitive coupling in an unbalanced line, you absolutely must place a shield around the wire and ensure it is solidly grounded at least one end. That grounded shield literally intercepts the electric field, shorting the displacement current harmlessly to ground before it ever hits your receptor wire.
All right, let's rapid-fire recap the essential rules you absolutely need to take away from this explainer. First, always visualize capacitive coupling as a phantom current generator firing displacement current across a gap, just like an invisible tuning fork. Second, memorize the core equation. V sub n equals j omega RC12 V1. Frequency, resistance, and capacitance drive your noise. Third, physical separation is your absolute best defense, and that very first inch of space does almost all the heavy lifting. And finally, beware the high impedance gotcha. If your resistance to ground is high, the math flips into a purely capacitive voltage divider, and frequency no longer matters at all.
Stray capacitance is just a fact of physics. You can never completely eliminate it, you can only manage it. So look closely at your current PCB layout. Are you leaving it totally vulnerable, or will you use these formulas to mathematically armor your signal path? Respect the spacing, mind the impedance, and please don't let invisible coupling destroy your next design. Hit subscribe for more deep dive EMC and engineering survival guides, and we will see you in the next explainer.